Now let us discuss the second application of Biot-Savart law. Magnetic field at an axial point of a circular coil. Consider a circular coil of radius small a that carries current I in anticlockwise direction when viewed through the right side. The plane of this circular coil is actually perpendicular to the plane of our screen. And the axis of the circular coil is on the plane of the screen. Suppose we have to calculate the magnetic field at point P on the axis of the circular coil. This is axis of the circular coil at distance x from the center O of the circular coil. For this purpose, consider a current element at point A, and the direction of dl will be same as the direction of current at that point. Now join point A and point P. There forms a right-angled triangle OAP. After joining, you have some geometrical values. Check there. AP is equal to R, OP is equal to X, and OA is equal to small a, the radius of the circle. And angle OPA, angle OPA is phi. And similarly, if we consider another element at diametrically opposite point of A, this angle will also be equal to phi. Now, the magnetic field at point P due to the current element at point A, as suggested by Biot-Savart law, is given by dV is equal to mu naught by 4 pi ideal sin theta upon r square. Here theta is taken as 90. Remember that dl is perpendicular to r because this r is parallel to the plane of the screen, plane of our screen, and plane of the coil is perpendicular to the plane of our screen, and dl is parallel to the plane of the coil, so dl is always perpendicular to r vector in this case at every point on the circumference wherever you take. So theta is 90 degree. Now after substituting this value, we get the simplified form in equation 1. dV is equal to IDL upon r square, and the constant term is mu naught by 4 pi. To get the total magnetic field at point P, we must first of all think about the direction of this elemental flux density. According to Biot-Savart law, we can predict the direction, which is perpendicular to the plane containing both dl vector and r vector. Obviously, the direction of dv vector is at least perpendicular to r vector, here we can say. So dv is directed perpendicular to this r vector, but it is slanted with the axis of the coil. So it has two rectangular components in reference to the axis of the coil. One component dv sin phi along the axis of the coil and dv cos phi perpendicular to the axis of the coil. If we consider the current element at a point diametrically opposite on the circumference of the circle, the magnitude of elemental flux density will be same, and the vertical component of that elemental flux density will have same magnitude but opposite direction. But the horizontal component adds up. So to get the total magnetic field, we integrate only the horizontal component dv sin phi of this elemental flux density. So we do not integrate total dv, only dv sin phi component of equation 1. Remember this. The vertical component dv cos phi cancels out. So we do not need to integrate total elemental flux density. Just integrate the horizontal component of this elemental flux density to get the total magnetic field at point P. Yes, so we integrate only the dv sin phi component. Now substitute the value of dv from the above equation. Yeah, it looks like this equation. Then see here, mu naught by 4 pi constant, current is constant, sin phi is constant, because sin phi is equal to a upon r. A is radius and r vector here in this case is constant because it is symmetric about the axis, so its value do not change throughout the circumference of the circle. And r is just root under a square plus x square by using Pythagoras theorem. So constant terms are taken out of integration sign. Now integrate only dl. Integration dl throughout the circumference means the circumference itself. So we replace that integration dl by value of circumference, that is 2 pi times radius. The radius here is small a, not r. In the previous case we supposed radius r because the radius vector, that is the line joining source point and field point, was the radius itself, so we suppose radius r. Here in this case radius vector is to be supposed or is to be denoted by vector r, so we denote radius by small a and the circumference is 2 pi a. Now by simplifying you get the result, mu naught ia sin phi upon 2r square. Again, substituting the value of sine phi a equal to a by r, you get mu naught I a square upon 2r cube. And this expression is also true for a coil of single turn, but in practice, coil has large number of turns. So if the coil contains n turns, then the total magnetic field is obtained by multiplying it with number n as b is equal to mu naught n I square upon 2r. Remember, r is root under a square plus x square. The direction of this magnetic field is towards the right, at point P, away from the coil, as suggested by right hand fist rule. Because we have considered the direction of current to be anticlockwise as viewed from point P, the direction of magnetic field is towards the right. Now, special cases. First case, if x is equal to 0, x0 means, remember that the field point is at distance x from the center of the circle O. If x is equal to 0, that means the field point lies at the center. So this must represent the previous case. Let's check. As r is equal to root under a square plus x square, r will be equal to, this is not approximately equal, this is equal to a. So the above formula becomes b is equal to mu naught ni square upon 2e cube. That is mu naught ni by 2e. Exactly the same result obtained in the first case at the center of the circular coil. In that case, we represent the radius by r. Here, radius is represented by a. Okay, let us see next case. If x is very greater than a, then we can neglect a as compared to x. R will be approximately equal to x. So in this case, the magnetic field will be given by mu naught ni square upon 2x cube. Thank you very much for watching this video. I will discuss other two applications of bias Sabart line next video. Keep on watching. Thank you guys.